Hi, welcome back. In this episode, we will go through a more concrete example of TLA plus. So really, again, right, like the TLA insight, the key insight to TLA plus is modeling a system as a state machine, right? And then so in this example, we will go through a modeling of a simple digital clock. So assume a clock, with a hour and minutes. So you have basically the possible value of the hour will be between 0 to 23, and the possible value of minute will be from 0 to 59. And so from a state transition perspective, hopefully it's obvious. So basically the state you go from 0000 to 0001, 0002, so on and so forth. And then so the I guess not the last state, right, but one of the state before you wrap around will be when the clock hits 23:59, then it sort of wraps around back to 0000, right? Hopefully a fairly straightforward state machine. I believe this is also an example used in the book written by Leslie Lampert, the Specifying System book. So in this particular example, each state only has one entry and one exit. It doesn't need to be like this, right? Just in this example, this is the state machine. There's no, like, the TLA language plus TLA plus language itself allows you to define a system where you have multiple entries into a single state or multiple exit from a state, right? That's all allowed, right? It's just that in this example, it's a one-to-one mapping. So in this example, we'll also sort of go through some of the basic, maybe the key features, I guess, of TLA plus, right? So for every specification, you can specify safety properties. So safety properties are properties that must be satisfied on a given state, right? So going back to this example, basically in every single state, you can safely assume that the hour value has to be between 0 to 23, and then the minute value has to be between 0 to 59. That would be a safety value invariant that has to be correct or true for every single state. And there are liveness properties you could specify in TLA plus as well. So liveness properties are properties that must be satisfied across a sequence of states. So, for example, one liveness property of the digital clock could be that the time always progresses forward. So you're currently at 10 o'clock. It should eventually make it to 11 o'clock, right? When you're at around midnight, 23:59, it needs to wrap around to 0000, right? So these are properties that are only verifiable across a sequence of state, right? It's more than one state, right? You have to look at multiple states to confirm that the certain properties are true, right? So these are liveness property you could describe in TLA plus as well. And finally, so once you have written the specification, you can use the model checker. So that's the TLC. So TLC is the model checker that you could use to verify, your specification, right? To make sure that the safety requirements, properties, or the liveness properties have been upheld throughout the execution of the model checker. Okay, so that's sort of the premise, right? And then so let's go into the actual specification in more detail. So on the left side of the screen, actually this is the whole spec, right? So hopefully it's not too overwhelming, right? And then so we'll sort of go through the individual sections, right? So at the beginning, you always need to describe a init state. So in this example, we only have two variables in this specification. We have hour and we have minute. And we assume we start at midnight. So the I guess the up angle here is the temporal logic AND. It's a logical AND. So it's saying that in the init state is when both hour and minute equal to 0. And yeah, and then so this symbol is defined, right? So the init state is defined to be when hour and minute, they're both equal to 0. And then how do the states transition, right? That's the next part. So that's defined by next, right? So next is the, I guess, the action associated with every single state. So notice that, this is I guess, a down angle, if you want to call it that. So we have two options, right? It's basically either next minute or next hour, right? And then, so basically in this example, the next hour means that this is what gets called on an hourly boundary, right? When we roll over to next hour. And the next minute is called when we are, just bumping the minute, right? Every minute. Then let's take a look at the, and then, so the other thing, the downward angle really is or, right? So you're picking one or the other, right? So either we're rolling over the hour or we're only bumping the minute. Then let's take a look at the next hour, or maybe let's start with the next minute more specifically. So in next minute, basically, then this is a collection of conjunction, I believe. So basically, these all need to be true, right? All these conditions needs to be hold for the transition to take, right? So the condition being minute cannot be 59, right? Because we need special handling for what the 59th minute, so to speak, right? We need to do the rollover. So that's the other case, right? So, but for any minute value that is not 59, so from 0 to 58 inclusive, we can take the next minute. Then the next two is really describing what happens in the next state, right? And I want to highlight here that the prime variable here means the next state variable, right? So basically this is saying that the hour value, the hour variable in the next state is the same as the hour value of the current state. So that's what hour prime equals to hour means here. And then again, this is a equality operator. This is not an assignment operator. This is a specification. We're describing the relationship between the current state and the next state. It's not an assignment variable, assignment operator. And then finally, the third conjunction in this function is minute prime equals to minute plus 1, right? So the minute variable in the next state is the minute value of the current variable plus 1, right? And then so the other one, the next hour, is really defined fairly similarly, right? So we only take next hour when minutes at 59, we're about to roll over, right? And then so in this case, the minute value in the next state resets back to 0, right? That's described by the lost conjunction in this definition. And then the hour value is increments, unless we wrap around, right? So in the midnight case, when it's 24, it wraps back around to 0. And really that's it, right? So this is a fairly, hopefully straightforward example of a TLA plus definition of a digital clock, right? And then so this again corresponds to this state diagram up here. So now we have the init being defined, and then the next action being defined. We need to define the actual spec, right? So the actual specification is defined to be basically a conjunction of the two, right? So we have, init followed by a box action of next, right? So here we go into a little detail of like what exactly this means, right? So the box, the box action formula, but in some sense, you don't really need to worry too much about it. Like all the specification that I guess I have written so far all take the same form, right? It's always, init followed by some sort of next definition. You probably want to include fairness, below this. But in any case, it follows a fairly similar boilerplate, if you will, that looks like this. So, so now we can sort of define the safety property, right? So as discussed earlier, one of the safety property for this particular system is, for example, the hour value and the hour variable and the minute variable must be bound within certain range of values, right? And then so that's described using the safety properties, right? So in this case, both of these conditions have to be true, right? So in the type OK definition, the hour must be within 0 to 23, and at the same time, so this is a conjunction, right? So both of these have to be true. Minute has to be within 0 to 59, right? And then so let's take a look at the maybe the actual syntax on the left, right? So on the right is the mathematical notation describing a TLA plus definition. On the left is how you will actually write it in ASCII, right? So there's a one-to-one lookup table you could refer to, again, going back to this specifying systems book authored by Liz Lampert. I think it's figure 8 that has the translation. But in any case, like, the translation is fairly trivial. But I do want to highlight that, like, basically on the right is how it looks like when it's rendered. On the left is how you will actually write it. But the mapping is one-to-one. What else? Right. So yeah, so safety is up here. Right. Okay. So now, again, right. So as discussed earlier, safety or like safety invariants are properties that have to be upheld in every single state. So this has to be, the type OK has to be true in every single state. But we need more than that, right? Like, we actually want to confirm that the clock, for example, always increments, right? It's the minute ticks, so to speak, right? And we want to confirm that. One of the behavior we can confirm, or the liveness property we can confirm, is that, for example, the clock does wrap around or roll over correctly at midnight, right? And then so again, there's actually a collection of operators you could use to sort of describe your liveness property. And in this case, we can use the leads to operator, right? So the liveness example here, we're basically saying that, when hour is at 23 and minute is 59, so right before midnight, if we're in this state, it will lead to midnight, right? So it will lead to a when hour equal to 0 and minute equal to 0, right? So we will wrap around, from 29:59 to 00. So this is a liveness condition we want to verify. Again, tying back to what we just talked about earlier, this is actually, in this case, we have at least two states, right? So the liveness property can only be verified, when you have a sequence of state, right? So basically more than one. And in this case, it's two, right? So basically 23:59 and 00. So two states. So one leads to the other. So that's good, but we're not quite done, right? So liveness is typically coupled with fairness, and then so basically, without specifying fairness, the spec allows inaction, so to speak. So there's no requirement. So unless you specify it, you're allowed. The spec allows the system to remain in the same state. So like, look at the right arrow here, right? Like, it doesn't. You have to basically indicate the system has to transition. Without providing that description, the system is allowed to stutter, I believe the technical term. Stutter means that the system can just do nothing. It could just remain in that state, right? So without that fairness description, the system is allowed to just stay at midnight, for example. So without fairness specification or fairness description, by definition, you can't really verify liveness, right? Because by definition, liveness is verifying a behavior, right? A sequence of states. So without fairness, the system is allowed to stutter, basically remain in the same state, and therefore all your liveness properties will fail without fairness description. So there's actually a bit more to fairness, right? There's weak fairness and there's strong fairness, and there's like subtleties on, when you want to use different descriptions. We're not gonna worry too much about that in this video. So in this case, just assume we'll just assume we want to use weak fairness. That's good enough in this example. We'll cover difference between weak and strong in a separate video. But in any case, right? So we want to augment our spec with the additional conjunction here, right? So we're saying that there's a weak fairness requirement to next, right? And then like for the sake of this example, just sort of interpret that as, something has to happen, right? You can't do nothing basically. So this description basically says that, like basically next has to be called, right? And then so with that, we are sort of forcing the spec to say that the spec has to continuously make progress, and therefore now we could verify our liveness property, right? Which is, like basically wrapped around correctly at midnight. Okay, so finally, so we got our spec. Our spec is complete, I think. So we could now verify the spec using the model checker. So I'm not going to go into, I guess, installing the model checker and then installing the toolchain and TLA tools and whatever. There's a TLA, so there's like a lot of online resources you could use to sort of figure out how to do that. The main TLA toolbox is a Java-based application. Again, right, like there are other materials that sort of goes through how to use that. And I personally I'm a more command line user. And then so in this series of video and everything referenced in the book, I'll be using the command line tool directly, the TLC tool directly. And then, but in any case, right, like whether you use the toolbox, the Java-based application, or use the command line tool, the input are the same, right? So you need the spec and you need the configuration file, and then you just run, right? And then just that the Java-based, like the TLA toolbox, gives you more of a visual feedback, right? But I believe they work the same. So you need two things, right? So you need a TLA spec. So in this case, clock TLA. Oh, and the other thing to highlight is the module name has to match the file name. Otherwise, the model checker will refuse to run. And similarly, you need to give it a corresponding configuration file, right? So we'll take a quick look at the configuration file here. So fairly trivial, hopefully, right? So basically, the specification is the spec. And then the invariant, so these are the safety properties. So this is, we need to make sure hour and minute value are all within bound. That's described by type OK, which covered earlier. And finally, property is the liveness property we just discussed earlier as well. Okay, so now we got the spec, we got the configuration, we have specified what we want to verify and what the spec looks like. We're ready to run. So, okay, so in here, my specification is saved under the TLA directory. So I run TLC, TLA clock. So again, right, like this is our environmental specific. I think if you go back to the book, it says you could, like, this is the whole command you want to issue, right? It's just that in my environment, this is already, saved as the TLC. The TLC command alias is to what's highlighted here. Okay, so now let's try to run this. That really is it, right? So if there's a violation, this will fail, right? And then so the graph in this case has 1440 or 1,440 states. This basically corresponds to the number of minutes that are in a day, right? So not hopefully nothing too surprising here. So we can again, right, tinker around with maybe I'll just modify the safety property, right? And then so what we even do? Yeah, okay. So why don't we just reduce the range, right? And then so we'll just confirm that So in this case, we're expecting this to fail, right? Because we know that at the end of the hour, the minute will be 59. Yeah, and then so basically, the model checker fails as you would expect it to, and then basically there's a backtrace that sort of leads up to, when the safety property has been violated. So that really is it. What I want to cover in this episode. So again, thanks for listening. Bye.